Welcome to part 2 of transformers. If you need a moment, go ahead and copy the diagram on the left. I know it's the same as the previous example, but we're going to use it in a different way, so you need a second copy of it. I'll give you a moment to do that. All right. Now, you're also going to want to have the result handy from the previous example. So if you already have it in your notes, just use that. Otherwise, you can recopy it here. All right. So a quick reminder of the last example. We had a large solenoid, that's the blue one, and a small one, that's the red one. And we put a changing AC current into the blue coils. And our goal was to calculate the EMF, the voltage induced in the red coils. And that's what a transformer is. It's a pair of coils with different amounts of turns. So we used several ideas to do this. First of all, we had an input current that changed, that was always changing as a sine function. We have Faraday's law. We know the equation for magnetic flux, and we know the equation for the magnetic field created by a solenoid. So this example uses a lot of stuff at a time. We calculated the magnetic flux going through the blue coil, and then we did the time derivative of that times n to find what is the EMF generated in the red coil, a little coil. And then if you wanted to find a current in the little red coil, you can then use Ohm's law, V equals IR. This is V, voltage. So what's different about this example? Okay, well, we're going to tweak this slightly. And then I'm going to also talk about some very easy relationships in transformers. So first, the tweak. Let's say instead of the input being the blue coil, let's say the input was the red coil. So I'm going to take this current, I equals I naught sine omega t, and plug it into the red coil. And I want to figure out what's the EMF generated in the blue coil. Now, I'm not going to redrive this whole thing from scratch. I'm just going to show what would change in our final result. And it turns out it's not much. All right, so first of all, going to magnetic field, well, now you'd have to figure out the magnetic field created by the red coil, which is B, okay? And all that would change would be, instead of an NA over an LA, it'd be an NB over an LB, okay? And then we'd have to figure out the flux leaving the big blue coil. So that would be flux equals the B created by the little dude times some area, okay? Now, here's where it gets a little tricky, all right? So the little red coil makes a magnetic field that looks something like this. And I'll kind of sketch that out. That's B of the little coil. That's coil B, which is actually the red coil. So this magnetic field would look something like this. Now, there'd be a little bit looping back around, but I'm not going to worry about that. All right, so we have to figure out how much flux leaves coil A, the big coil, all right? Well, the magnetic field strength is changing along this area. So it'd be really hard to do magnetic field strength times area to find flux for the blue coil, because that magnetic field is not constant along that area. However, if you look carefully, every magnetic field line that leaves the little guy also goes through the big guy. And here, for the little guy, the field is fairly constant along this area, okay? So the magnetic field, the magnetic flux leaving A, the big coil, is equal to the magnetic flux leaving B, the little coil. And so how would we calculate that? Well, going back to our previous example, this magnetic flux would be the B made by B, which we already calculated, times the area of A, okay? I'm sorry, times the area of B, sorry. So this equation would change, only this would become, instead of an A, it's now a B. In other words, these both became B's, okay? So far, the only thing we've changed is, instead of NA and LA, it'd be NB and LB, okay? And then we'd have to find the EMF in the big guy. And EMF, we would use this equation again. The only things that would change would be, this would be the change in flux leaving A, okay, which we calculated, but we used B to do that, and this would be NA, Okay. So it turns out if you rework everything, the only thing that would change in this whole entire equation would be this. Instead of an LA, we'd have an LB. Okay. I mean, technically, these two would flip flop, but that doesn't matter. And it's still the smaller area. You're still using the area of this solenoid because we know the magnetic field strength is relatively constant along that area, so we can calculate the flux leaving. So that would be the only change. This would turn into an LB, and otherwise the equation would be identical. Okay. Now, there's a couple easy relationships for transformers. So looking back at our pictures, okay, you'll notice that in the real life transformer up here, this is the one behind my house. The skinny wire up top there, that's the high voltage line that runs around LaGrange. And that's about 5,000 volts or so. I'm not sure of the exact number, but I know it's roughly between 5 and 6,000 volts. So these skinny wires that go into this transformer are at like 5, 6,000 volts. Now, the wires that leave this transformer are 120 volts. Okay. So this would be called what we call a step down transformer. It's reducing voltage. Well, it turns out there's a really easy way to calculate output voltage if you know input voltage. So this example here, we saw that all the flux leaving the little guy also left the big guy. Okay, so they share the same flux. Okay, so if we write out Faraday's law, EMF is N d magnetic flux dt. Now, I'm skipping a negative sign here. I'm just worried about magnitude. Okay, the flux leaving both solenoids is the same. Okay, so if I solve for the change in flux over time, that's the same for both things. Well, this is E over N. Okay, so that ratio is the same for both solenoids. So what we can write is we can write E of A over N of A equals E of B over N of B. Or very simply, the voltage in the coils is directly proportional to the number of turns in the coils. Now, you'll often see this written as VA over NA equals VB over NB. Same thing, okay? Or they'll flip it around and they'll say like V secondary over V primary equals N secondary over N primary. Quick note, primary, I'll write that down for you. That's the input. And secondary, that's the output. Okay, so you get this really easy equation for transformers. The voltages are proportional to the number of turns in the coils, or how many coils you have. So a step-up transformer has more coils in the secondary than the primary, and a step-down transformer has fewer. Example of a step-down transformer would be like your cell phone charger. A step-up transformer, ComEd has, or your power company has those. Usually, power in the power company is generated at something on the order of 5,000 or 6,000 volts, and then the transported across states, they step it up to often several 100,000 volts, and then step back down. So you have step up and step down transformers. Now, another really easy relationship to understand is that at best, the power in the primary is equal to the power in the secondary. Now, that would be if you have a 100% efficient transformer, which none of them are. But if we assume 100% efficiency, then that's the relationship you get. And you might recall electrical power is I times V. So I in the primary, V in the primary equals I in the secondary, V in the secondary. Now, a consequence of this, if let's say, for instance, you have a step-down transformer, if voltage goes down, then current has to go up proportionally. Okay, so you don't get a change in voltage without changing the current as well. That's why, for instance, in our real-life transformer here, the high voltage wires are really skinny, whereas the lower voltage wires are thicker. The lower voltage wires actually carry more current. Okay, so that's why they have to be thicker. You'll notice the same thing in this diagram here. They did a really good job. The input, here's another step-down transformer. The input's got a lot of turns, but they're skinny wires. The output is a lower voltage, but a higher current, so the wires are thicker. Okay. So you got those two relationships, and they're very, very simple. Okay. Now, one last comment I'll make: why for instance, your power company, why do they have voltage generated at 5 or 6,000 volts, and why do they step it up to 100 or 200,000 volts across the state? Why? Because it's so dangerous to have that kind of a voltage. Well, when you transmit power from one place to another, the energy you lose in the lines is proportional to I squared. In other words, the power loss in the lines is I squared R, R being the resistance of the actual wires themselves. Well, if you step the voltage up a lot, then you can reduce the current a lot, and you end up reducing all that extra heat. Matter of fact, we couldn't operate our modern power grid if we did everything at 120 volts. The power lines, so much current would have to be flowing through them, they would literally melt off the line. So we need that really high voltage so that we can have less current, so that we can actually transmit our power from one place to another. I hope that was helpful. See you next time.